All right, 2.12, logarithmic function manipulation. And Mary's going to read it.
Since logarithmic expressions can also be written in exponential form, the same properties that apply to exponents can also apply to expressions involving logarithms. These properties allow us to manipulate logarithmic expressions to form equivalent expressions that may be useful when solving equations or graphing functions involving logarithms.
All right, fantastic. And so a product property. So if we have multiplication, that's addition between the logs. All right, and if we have addition, if we condense it, we'd have what? Multiplication. All right, and then so this one, if I have log of x over y, that's really what? Subtraction. And subtraction is really division. Okay, now I want to extend that one. I'm going to say it's like x, y, z. And so I'm going to put a z on the bottom too. And so is that going to be plus log or minus log? It's going to be minus. And the reason why is because it's also in the denominator. All right, and so that's why it's minus z. And then we have a power property. This is kind of what I wanted to refer to the other day. However, we just didn't learn it yet. And so if we have an exponent, that's the same thing as our coefficient. And if it's our coefficient, guess what we could do? We could substitute it back in to be our exponent. All right. Now, I kind of want to go a little bit further to prove this quotient rule. What is my coefficient of this negative thing? This would be a power of what? -1. Is everybody following me? And so if I were to put a -1 on this exponent, guess where it goes? In the denominator. And so that's why they kind of like form together rather than they repel. All right, keep going, Mary. You're doing great.
These properties can also be used to show that various transformations of logarithmic functions can be written in equivalent ways. Example, for each of the following, write an equivalent expression by condensing each expression to a single one.
All right, so the first part, we have addition going on. So what does that imply? Multiplication. So now we have log base 4 of xy because they multiply. All right, let's look at part B now. So now we have subtraction going on. So what does that imply? Division. So now we have log base 3 of what? 5 over z. All right. All right, let's look at part C now. And so now I have all of these. And so I have minus log 5 and minus log z. And so now, who gets to stay up top? X. Who gets to go to the basement? 5z. All right. Pretty good so far? Cool. Let's look at part D now. So now I have 3 times log base 2 of x. Well, what does that 3 do? It's an exponent, all right? And so this is our exponent rule, or our power property. And so now this would end up being log base 2 of what? Who gets to go up top? X cubed. All right, x to the third, because this is our power. Our 3 is our power. And so now it's over what? Y. All right. All right, let's do the next one. And so now, what does this 2 really represent? An exponent. So this is really a squared. And then this 5 is really a what? An exponent. So this is really b to the 5th. And then this is really log just 4. All right, and so here we go. And so now I have log of 7. And then who gets to stay up top? I get a squared and what else? 4. And so I'm going to write it as 4a squared. And then it's over b to the power of 5. All right? And so that's how we'd condense that one. All right, let's look at part F now. This one's a little bit tricky. And so it says in our notes, it says to say it is a single logarithm. Well, how many terms do I have going on right now? I got 2 terms. And so is this 2 a logarithm at all right now? No, I'm actually going to convert it into a logarithm. So this is what we're going to do. And so I want it to be a log base what? 6. And so I'm going to say log base 6 of something, and I'm going to call it a b, is equal, sorry, it's log base 6. I'm sorry. Did I say 6? And then I wrote 2. That was silly. So log base 6 of b is equal to 2, because I want it to equal 2. Well, how do I solve a log? A to the c is equal to b. So what's my a? 6 to the power of 2, which is equal to b. And so so what is 6 squared? 36. So now I'm going to take this 2 and replace it with log base 6 of 36. And then I have plus log base 6 of x. All right. You see how I just had to do a little bit of work to convert this 2 to make it a log? All right. And so now, what is log base 6 of 36 plus log base 6 of x?
Log base 6.
Log base 6 of 36x. All right. All right, cool. Let's look at example 2 now. So those were all condensing in example 1. Now we're going to practice expanding. And honestly, in calculus, we expand more than we condense. We condense sometimes, but anyway. All right, so this one I have log base 3 of x squared over y. And so how could I kind of expand this one? This would be log base 3 of what? X squared, right? However, do I really want x squared? No, I just want x, but where's the 2 go? In front. So now I have 2 log base 3 of x. Now, do I add or subtract when I deal with this y? I subtract. Tell me why. Because it's in the denominator. So now I have log base 3 of y. And so which one does that look like? C. All right.
Example 3. The function f of x equals log in parentheses 6x is a horizontal dilation to the function g of x equals log x. Show that f can be also written as a vertical translation of g with f of x equals g of x plus k, where k is constant.
All right, fantastic. So I want to talk about the horizontal dilation real quick. And so this isn't asking this one exactly, however, you will kind of have these on your homework set. And so log base 6x, it's a horizontal dilation, but it's a horizontal dilation by what? 1/6, okay? Because that's going to come up later on. However, they're saying, yo, make it a vertical translation. And so what's happening here is that they want me to expand this log of 6x, all right? And so g of x is equal to log x. So what we're doing here is we're going to say log of 6x is equal to log of x plus something. And what is that something? How would I break up this log of 6x? What's happening with 6 and x? They're being what? They're multiplying. So what can I do? I can add them. And so then I'd have log of x plus log of 6. Now, does it ask me to solve for k in this one? Not really. However, what is k? Log of 6. Log base 10 of 6, which is just a number. It doesn't ask us to find this number, but it's just a number. All right, cool. All right, so now we're going to talk about change of base. All right, I'm going to spend a little bit of time on this one. So I have this log base b of x is equal to log base something of x over log base something of b. And I kind of want to break this down a little bit, and I'm going to use numbers right away. And so let's just make one up. So I have log base, what do you want it to be? Ethan? What's your favorite number?
Like 3.
Is that your soccer number?
No.
What's your soccer number?
9.
9. Log base 9. Oh my gosh, we're going to use log base 9 in the next one. All right, so log base 9 of, what's Alejandro's number? 10. Log base 9 of 10. Here we go. And so if I change of base this thing, the way we can do it is we can have log base whatever we want. What base do you want? Let's just say 3 in this case, of 10 over log base 3 of 9. And so the way we do our change of base is we have this like our of over our base. And we can make it whatever base we want here. And so a lot of the times we don't necessarily need to pick these 3s. In calculus, I'm just going to use natural logs most of the time, and we can be fine with it. And so this is the same thing as like natural log 10 over natural log 3, or sorry, natural log 9. And so this log base 9 of 10 is the same thing as natural log 10 over natural log 9. We can pick whatever base we feel like it, all right? But it's always the of the b thing over the a thing, all right, in the way that we normally do it, all right? All right, so let's look at example 4.
such that f of x equals k times g of x.
All right, fantastic. All right, and so let's kind of write this out. Okay, so f of x is equal to k times g of x. So f of x was given to me as what? Log base 4 of x, right? That was f. And then it's equal to what they call k times, what is g of x here? Log base 9 of x. All right. And so they're kind of telling me which way to go. Okay, I need to get a log base 9 of x. And so I'm going to convert this log base 4 of x into base 9. Does everybody follow me on this? All right, and so this is how we do it. So we're going to use a change of base. And so I'm going to manipulate this one. And so log base 4 of x, I'm going to say is the same thing as log base 9 of x over log base 9 of 4. Do we see how we changed to base that thing? Okay, so we can call it any base we want, and we're just going to call it a 9 here. All right. So what is going to be k? So if I had to kind of make it like this, I have a log base 9 coming out front. So what's my constant multiple out here? I need to divide by log base a of 4. So this is really 1 over log base 9 of 4. And so guess what k is? 1 over log base 9 of 4. And there we go. All right. And so that's how we use change of base. All right. We'll use change of base for other things, but that's what we manipulated there. All right. All right. We kind of talked about these already a little bit. So a natural logarithm is a log base what? E. All right. So if they have a log base e, that's a natural log, and natural logs work the same way regular logs do. So we need to find out what's equivalent to 3 natural log x minus 4 natural log y, and so we're going to condense this one into our single logarithm. So what's this 3 do? It's an exponent. All right, and so now we have a natural log of x to the power of 3. And then what's this subtraction doing? It's dividing. And so it's over what? Y to the power of 4. And so now I look for that answer, and what does it match up with? A. All right.